Thanks, everyone. Thanks for coming. Can you hear me okay? Cool. Yeah, so I'm Chris. I work at Driven Data. We're a data science consulting company. We also host machine learning competitions for social impact. And I'm going to talk about kind of a case study of a project that we worked on recently that I think there might be something to learn from that made a public data set a little bit more accessible. So we'll cover what I think this case study is an instance of, which is what I've come to call the last mile public data problem. Essentially that public data sets, who here has worked with a public data set? Okay, yeah. And has it been in a format that's been like super easy to use and just like ready to go? Rarely. This is something I've often encountered as well. And it's really frustrating because it makes it so that you can't actually access the valuable information that these data sets contain, and it makes it harder to justify or encourage the future or continued collection of data. And then I'll share a Python package that we made in collaboration with another organization called Science for America called SciPeds that is specifically looking at education data in the US, but I'll try to abstract out a little bit and point out things that you might be able to take forward when applying this to other kinds of data sets. So what I hope you'll take away: baking data, bringing it closer to tooling for analysis is a great way to improve the accessibility of these data sets. Talking to users about what questions they have and the things that they want to analyze is also a great way to design things that are actually going to get used. And Python and DuckDB as a combo is cool and fast and flexible, and you can do all sorts of stuff. So I probably don't need to tell you all this, but the fact that you make something public doesn't necessarily make it accessible. It's what I'm calling the last mile public data problem. I don't have a problem with public data. Public data is great. Love it, want more of it. You can go to all of these different data portals from all of these different countries or governments or organizational bodies, and it's great. It increases transparency, it increases our knowledge about the world. And I think there's a fairly straightforward rationale for why public data is good as a public good. Things happen in the world that we want to know about, and so we collect data about them. And then while we've gone through the effort to organize and curate and collate all of that data, we might as well make it available for other people who want to use it, because then they can ask questions about it and interrogate it and use it for their own purposes. So it gives information to people who want it. Otherwise, why would you bother making it public? The problem comes in this publication to usage transition. I often find that the data is made available in a format that reflects the collection process rather than a format that makes it conducive for analysis. And that is a barrier even for people with technical knowledge to be able to kind of munge it into the right structure. But it becomes even more of a barrier when people who don't have the technical expertise or knowledge are trying to use this data and get it into a format that they can actually work with. So having been faced with this multiple times, I had this question of like, is there a way to try to tackle this problem that makes this a little bit more tractable, that makes it a little bit easier for us to deal with it? In working on the case study that I'll share, I came across this concept of baked data, which is not my idea, it's not my term. Simon Willison came up with it back in 2021. He published a blog post about a baked data architectural pattern in the context of web apps and web deployment. And what he called baked data was this idea of bundling a read-only copy of your data alongside the application code as part of the same deployment. And this sort of baked data infrastructure kind of takes the traditional deployment architecture where you might have a hosted database layer and a hosted application layer that are separate from one another that need to talk to one another over a network, and it combines them, and it packages them up into the same thing. This comes with trade-offs, right? The packaging layer is not infinitely scalable in the way that the database layer is. There's other considerations, but what it does do is it brings the application code and the data closer together, which means less overhead, less like data transfer requests, and you can have a tighter coupling of both of those things together than you might otherwise be able to. And so that got me thinking about trying to use this concept of baked data tooling and apply it to this last mile public data problem. And the way that I thought about applying this is, can I take something that is maybe structured in a way that reflects collection and transition it into something that's a lot more easily queryable, maybe it's relational, something that's really well structured that I can analyze quite easily. And that's what we ended up doing for a library that we built called SciPeds. SciPeds is a product of my organization, Driven Data. You might know us from Cookie Cutter Data Science if you've ever used that package before. And Science for America, which is a nonprofit that's trying to focus on improving access to STEM and STEM education and basically science in America, which needs it. Science for America in particular was interested in looking at STEM education in colleges in the United States. And they were interested in a few different questions around representation, both race and ethnic representation as well as gender representation in a variety of different STEM fields and trying to look at this over time. And good news, there's this resource called IPEDS, the Integrated Post-Secondary Education Data System, which collects just a ton of data about higher education in the United States. So it's a great resource. They had this question, you know, how has the number of women studying STEM changed over time? Fairly straightforward question. When you go and look at the data page looks like this. So just for 2023, this page scrolls on and on. You have starting out with institutional characteristics, but then going on to enrollment, completions, all of these different types of data sources in a variety of different formats with their own data dictionaries. So it became quite clear early on that it was not going to be easy or straightforward to try to parse and analyze each of these data sets to come up with an easy answer to this question of how representation has changed over time. In addition to that, the schema for categorizing things as belonging to science and technology, engineering and mathematics education or not have changed over time. There's all sorts of nastiness in the evolution of the schema that happened, which are hard to take into account if you don't have the right analytical tools. So what we ended up coming up with was building a Python package backed by a DuckDB database. And we made that DuckDB database file kind of standalone and portable so that it can move with the package into a variety of different contexts, whether those are user-facing or whether those are behind the scenes on the back end. There's also a pipeline application that I'll get into in a bit that collects all the data, organizes it, and generates this file so that that DuckDB file can be versioned along with evolutions in the code base or corrections or changes. So what does SciPeds look like? So this is an example of trying to look at degree completions in the United States. And we are particularly interested in STEM bachelor's degrees awarded to men and to women. So we have this notion in SciPeds of a query engine. This is something that we can use to query completions data. We have this notion of a taxonomy rollup, which is essentially how is it that you actually define science and engineering? What specific fields do you include? Different organizations have different schemas. The Department of Homeland Security has one for immigration purposes. The National Center for Education Statistics has a completely separate one, and the two sort of overlap, but they sort of don't. So we have these built-in notions for how to refer to these things and allow users to select different taxonomies and different subfields within those taxonomies to include. And then we also have this notion of query filters, which basically allows you to say, oh, I only want to look at bachelor's degrees or something like that. And then we have built-in queries that you can use Python functions for. Essentially, these are wrappers around SQL queries that are dynamically generated at call time. So you can come up with any combination of different kinds of filters or subfields that you want to look at. So here we're looking at gender within a specific definition of science, and we're only looking at bachelor's degrees. And so we can look, we can see the number of degrees awarded within each gender, and then also the total number of university degrees awarded overall. And this is substantially easier than trying to go into the variety of different Excel files, pull out the definitions, do all of that filtering without access to these kind of pre-baked standardized tools. So a couple of things that I want to call out here that I think might be possible to abstract away as you're thinking about ways to apply this to other kinds of public data sets. One thing that our Science for America collaborators sometimes found frustrating was the way that bachelor's degrees are recorded in the data changes over time, and having to remember the different variable names or the different spellings of the different fields got really frustrating. And so we were able to just build a set of standard enumerations that gave clarity and consistency to the way that different concepts were defined and the allowable values for these different concepts. So we can do all sorts of validation on the queries by saying, does it belong to something in here? If not, we can throw an error to the user that's a lot more readable and a lot more easily interpretable. We also kind of abstract away the SQL part. So if you know a little bit of Python and you can get by, but you're not as comfortable working in SQL, you can kind of work your way around this without having to know that under the hood, it's querying DuckDB and you're getting all the benefits of OLAP processing on your aggregations without having to think about it at all. So behind the scenes, what we actually do to structure this database, it's basically a standard data pipeline. We take all of the different data files. There's a bunch of CSVs, there's Excel files, there's HTML files defining data dictionaries, which were just super fun to parse. And there's also a lot of different crosswalks that define how the schema that categorized education codes from 1990 to 2000 translates to the one that defines them for 2000 to 2010. So we account for all of these things, and then we write them to these intermediate compressed files. And then DuckDB has really convenient tooling for being able to take a bunch of different files and read them into a structured database. And if people are curious, we can dive into specific sections of the code that get into this. Happy to chat more about it later. We end up with something that has around 22 million rows, and it's 320 megabytes. This is not a big file. This is not like terabytes and terabytes of raster data that we're talking about, but it is somewhat complex because it's relational. There's relationships between different tables, institution metadata feeding into the completion so that you can see what the name of the university is, and being able to handle all of that in a compressed and standalone way has been really useful in a few different contexts. So one of the reasons that I say that this was inspired by baked data and not exactly baked data is that there's a 50 megabyte limit on packages in PyPI. And so we couldn't just like bundle this up as part of the actual library or package itself and deploy it. We do something that's a lot more similar to like load dataset from Seaborn or Hugging Face, where we give users the ability to download stuff. And what we actually do as part of our release process to ensure that this tight coupling works is we generate this DuckDB file as part of our release workflow in GitHub Actions. So we run the full pipeline on the worker that's processing the release. We stick it in a Google Cloud storage bucket, and then you can either download it if you're in a notebook environment, you can use Python. If you're at a CLI, you can use the CLI. So we give people lots of different ways to download data. They can also, if they want more granular control over where they're doing it, they can put it in a particular place. But otherwise, it'll just do the thing that you hopefully expect it to do by default. And okay, we've done a lot of work. We've written a lot of code. What has that gotten us? It's gotten us to a point where in a couple of lines of code plus some plotting libraries, we're able to much more easily ask and answer some of those questions that would have taken a lot more effort before we built this library. So specifically, in answer to the question, how has the number of women studying STEM changed over time, we can just say, okay, let's filter by bachelor's degrees just for the sake of having something that's standalone. And then we can look at, we can set the by year quark to true, and that will give us results by year, subject to all of these different filters. And now we end up getting this plot, which shows that starting off in 1985, men and women were getting about the same number of bachelor's degrees in the US. Men were getting more STEM degrees than women. And even though women have caught up and eventually surpassed men in terms of the number of STEM degrees, they've wildly outpaced them in terms of the number of bachelor's degrees overall. And this sort of quick and dirty and easy analysis is a kind of thing where now someone with a little bit of Python can come in and tweak this query and be like, oh, what about just computer science? What about just engineering? Let's see how that looks. And they have the ability to do that. So one thing that this baked data architecture also enables us to do is it makes it easier for us to port our data over to different environments. So for instance, the first thing that you'll see if you go to docs.scipeds.org is the fact that you can just spin up a Colab notebook. And in the Colab notebook, you download the data to the Colab data folder, and then you can do all of the same things. One of the big barriers that we've seen to people being able to make use of data, even if they do know Python, is just getting a Python install on their machine. That seems to be a huge barrier to just ordinary people trying to get access to this stuff. And by having it in something like Colab, we're able to democratize that and make it a lot easier to access that data. One of the things that we're also able to do, and this was, I think, the thing that was really, that I got really excited about is, let's say you don't have any technical knowledge whatsoever, you don't know Python, you don't know SQL, then you're still SOL because you can't access this data. And so what we ended up building was an interactive web app with Plotly. And rather than having to stand up some sort of complex infrastructure to do that, we essentially, with like a backend database that doesn't really scale that well, depending on different settings and different hosting providers, we just put the DuckDB file on the web worker. And now we have a web app, which hopefully I'll share and hopefully it'll work. So if you go to scipeds.org, you can see this is the website running live. It's got 2 CPUs and 4 gigs of RAM. And all of these queries are running live against the backend database that has all of those rows and all of the complexity that data has. Did anyone go to school in the US? Anyone want to shout out a university that they're curious about? All right, let's see. It's hard to type and hold the mic at the same time. Okay, so at Montana State University, what we're seeing on this visualization is for engineering programs, whether more women got degrees in engineering than got degrees as a proportion of the overall school's population, or fewer. And in this case, it looks like it's a factor of, what is this, like a little more than a factor of 2 underrepresented. Anyone else want to shout out school? Brown, great. Cool. So Brown's a little bit closer to parity in terms of representation, but this is all of the queries to generate these visualizations. Let's see, we can take a look at computer science. So on the back end, on the web worker, it's filtering through the DuckDB database. There's all sorts of additional filters. So if we want to look at like a range of dates, let's say we want to look at the last like 5 or 6 years. So this is crunching through a non-trivial amount of data. It's not the fastest. It could be faster if we increase the computational power of the web worker. But the fact that it's all happening without having to stand up really all that complex infrastructure, this is just a Plotly Dash app, is kind of cool to me. So we can also look a little bit more in depth at a particular institution. So let's go, sorry. Was it Billings? Oh, sorry. I need 2 hands to be able to type. Can you say it again? Sorry, can you say it again? Just perfect. Thank you. Thank you so much. Yep. So we're able to generate different plots for different fields. We're able to break down by gender and by ethnicity. We're also able to see kind of where how Montana State compares to other schools in terms of the representation of women within the institution or within the field. And then we're able to generate all of these different time series. So someone with no technical knowledge whatsoever can come in and get a lot of information about the way in which different groups are represented within their school or within their university. And it was reasonably easy to set up. If we did run into scaling issues, one of the benefits of this approach, here, I'll get into this in just a second. So I wanted to close with some thoughts on benefits, limitations, and use cases. I think this is pretty obviously not applicable to every single kind of public data or every single kind of problem. I know that I would have found this useful in the past when I was looking at kinds of public data sets like transportation data or policing data. There's a lot of different contexts in which I think this could be useful. It's really flexible. You get consistency and standardization. Deployment is pretty simple, and it scales really nicely horizontally because you can just spin up as many web workers as you need to serve different folks. I think the key limitation of this is I think we're probably data size limited. And for now, as I'm conceptualizing it, it makes the most sense with structured data. I could imagine using it perhaps in different contexts, but I'd have to think about that a little bit more. And then the other problem with public data is figuring out hosting, and who pays for hosting can be a problem, and this still falls under that body of this is sometimes a problem. So I think if you do have a reasonably complex, small to intermediate size data set, I'm capping this at 100 gigs for, I think that's probably still too big, but I could see if you had the right use case potentially being able to use it with things like that. And if you have an engaged audience that wants to be able to interrogate these data sets, but maybe have a variety of different technical knowledge. So maybe some people have some Python, maybe some folks have some SQL, maybe they have neither. This approach gives you the flexibility to address all of those different audiences and kind of meet them where they are. Okay, I think that's it. So we covered last mile public data, why it's important, public data is good, and we talked about this particular example. So I hope that you'll take away that baking data is a great way to make public data more accessible, that interacting with users during that process leads to better outputs, and that Python and DuckDB are cool, fast, and flexible. Thank you so much, and happy to take any questions.
Hi, thank you for the call. Very, very interesting. I was wondering if you are versioning the application alongside the data set, does that mean that you have duplicates of the data for every version, or you're just overriding every time?
No, we create a new version so that people can still download the old version if they used it for an analysis and they want to be able to reproduce those results. So every release, we essentially have a release version of the data set that we name, and we maintain separate copies of each.
Okay, but I imagine you keep a cap on how many if you have like a very large data set.
Yeah, if the data set were larger, I think we would want to be pretty mindful about storage. I would have to think about ways to do that. I imagine that there are some, but definitely.
Thank you.
Hi, thank you. So this is like a very good package solution for one data set, and my question is, what would be the building blocks you would recommend if tomorrow I wanted to do that for another data set? Because it feels like it's solving many orthogonal things, right? Semantic layer maybe, performance, database, visualization. So how would you split that into like the core valuable building blocks for another data set?
Yeah, I think probably the library piece, like it starts with the pipeline, because the pipeline is the thing that you need to turn something into an analytic ready data set regardless. And And once you have a DuckDB file, you could just query that with SQL and kind of be on your merry way. It kind of, depending on the level of accessibility or usability that you need, you can go further and further up the technical chain, and you can say, well, I want to design for people that don't have SQL, so I'm going to write some Python wrappers, essentially, that are convenience functions around what I imagine to be common use cases. And then beyond that, okay, people don't know Python, then I'm going to design these visualization layers. So I think you can starting with the pipeline, you can then move down the technical chain.
So thank you for the talk. So can you give a rough estimate of the effort that you had to put on every one of the single steps and how big the team was? So.
Yeah, the team was me for the technical side of things with my Science for America collaborator. I say that in jest. My Science for America collaborator, Claire, was guiding the effort and I was doing most of the technical implementation. She had like a bunch of pandas code and a bunch of notebooks that we kind of converted into this. So there was a really good starting point. This happened over the course of several months of me and her working together. I would say it probably took 3 to 4 months to get to like the MVP for the library. And then adding some of the additional layers on top of that took another couple of months.
Thank you for the good talk. When you spoke about web workers, are you using a remote web worker, or is the database being downloaded by the browser and running DuckDB WASM?
No, it's being downloaded by the web worker. Like the render worker, when it deploys, downloads it and deploys it as part of it. So it's running server side. It's not running client side. Yeah, I thought about that, but the problem with some of these queries is that they're using the whole data set. And so if you were trying to fetch something and then get it locally for processing, I think you would still have to you would have to download sometimes quite a bit of data. It's not huge, but it's enough where it feels slow.
Thank you for the talk. You mentioned that every version you are storing the data in the cloud bucket or something, but how do you test them in case of something changes inside the data itself? Because you also mentioned that sometimes you can't reach where you download it and etc. Something can happen.
Yeah, there's some validation tests that we do also as part of the release process. Where we test against like dummy data for the library functionality, but we also do some essentially like asserts on the main data set where we ensure that like columns exist, that the data has the rough size that we expect it to have. So after we generate the DuckDB file, we do some sanity checks before we like officially release to make sure that things work the right way.
If there are any more questions, maybe you can take them later.
Yeah, great.
And let's thanks the speaker one more time.